1.89 gigajoules. Because 10 to the power 9 is 10 to the power 9 is giga. So that's the potential energy, negative 1.89 gigajoules. Now, the kinetic energy, we don't have to recalculate it. We already talked about that. So the kinetic energy is essentially going to be half of this, but the positive. And then so it's just going to be, divide that by 2. So it's going to be positive 0.94. Let's do 1.89 divided by 2. So 0.945 if we round it. 0.945, let's say, gigajoules. So I'm rounding this to 1.89 and half of that will be 0.945. And then the total energy is going to be just this plus this. So 0.945 minus 1.89, and you're going to have negative 0.945. So the negative of this. Okay, so that's his total energy, kinetic energy, and potential energy. So let's say part C, we answer this kind of a question, something like this. How about if this satellite was losing the total energy somehow due to some sources? It was losing its total energy at a rate of so assume satellite is losing energy at a rate of, so let's say something like this, 1 megajoules per day. I know that maybe that's a lot, you know. So let's say it's losing total energy at a rate of 1 megajoules per day. So what's going to happen here? It's going to spiral inward, right? So how many, let's put it this way, how many years or how many days will it take? How long will it take for the orbital distance to get halved? How long will it take for the orbital distance to get halved? So half of whatever its original distance was. So we could do a certain calculation, right? So the total energy was negative 0.945 joules, gigajoules, right? And then here we can subtract from this. So we can say like this. This is the E initial plus the change in energy, the loss of energy, is equal to the E final, which equals negative GMM over D nu, the nu D. Right? So that's going to be our setup there. So the initial energy minus 0.945 gigajoules, and then it's losing, so you're going to subtract from that more, right? It's losing total energy of 1 megajoules per day. So how many gigajoules is that? 0.001 gigajoules per day times the number of days. So let's call that n. Or, the number of days n. So the answer that we get will be in terms of day. So we have negative 0.945 gigajoule minus, 1 megajoule is 0.001 gigajoule. per day times the number of days n. That's equal to, on this one, the d nu is half of the original d, right? So you could say negative GMM over half of the original d, and so this is simply going to be negative twice the original GMM over d, right? So remember, what was the GMM over d? That was the original potential energy, which was double the, it was 1.89, right? So just this itself, just this thing, was the gravity times the mass of the Earth times the mass of the satellite over the distance was 1.89 gigajoules. And then this is just simply twice that. So it's going to be, the new energy is going to be lower by a factor of 2. It's going to be 2 times 1.89. So you're basically then left with what? You have here, that one goes over here, and then this one goes over there. So it was 2 times 1.89 gigajoules minus 0.945 gigajoules is equal to, this thing goes over there, 0.001 gigajoules per day times an n days. So day and day cancel. So you're basically left with this one, gigajoule, gigajoule, gigajoule cancel. So you're basically left with doing this 2 times 1.89 minus 0.945, subtract by 0.001, and that's it. So n is equal to 2,835 days, and divide that by 365.25, 7 years, 7.76 years. So roughly about 8, close to 8 years. So that satellite is going to approach the Earth in about 8 years. It's going to be half the distance, okay? So that's why you have to make sure it's not losing energy due to any kind of source, maybe battery life or anything like that. Eventually, a lot of satellites do that, and so they come inward and inward and inward, and eventually they crash back into the Earth. Okay, let's ask another question for this situation. Interesting question. Call this part D. What would the period of the Earth have to be in order for people standing on the surface of the Earth to no longer be standing, to fly off? So if somebody is here, right, standing on the surface, let's say the Earth were to spin faster, 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 and spin at such a rate that the person could no longer be attached to the surface. So what would that rate have to be? So you basically argue here, you have mg, and do a little physics 1, and the normal force. In order for a person to no longer sustain themselves on the surface, the normal force would go to 0. Okay? And if the normal force goes to 0, you are no longer attached to the surface. And so you basically fly off and you'll feel weightless. So mg would have to equal mv squared over r. And if I want to calculate this in terms of period instead, I could use the other form, 4 pi squared mr over t squared. This is the other form of the centripetal force equation, expressed in terms of period. So m and the m cancel. And so the period would have to be what? Period squared is equal to 4 pi squared r over g. Now remember that the little g is equal to gm over r squared, right? As we have shown. So this is simply a restatement of the Kepler's law that we developed. 4 pi squared gm r cubed. The